Let's talk a little now about computer data formats. And talking about computer data formats, we can talk about the ASCII code, which is American Standard Code for Information Interchange, and we can also talk about Unicode, right? These are the two codes by which we can represent the computer data. So for example, if we talk about the ASCII code, we can look at table 1.8, which is given over here. And over here we can find the ASCII code for each character that we want. For example, if we want to find the ASCII code of B, the ASCII code of B would be 42. For example, if we want to have the ASCII code for the character $, it would be 24 or 24, and so on and so forth. So basically ASCII code would represent characters in memory. If you want to store any character in memory, we are going to be storing the ASCII code for that particular character. So this is important because whenever we take input from the computer by using any of the interrupt routines of INT21H, for example, if the user presses 9 on the keyboard, it is not 9, it is the ASCII code of 9 which is returned by the interrupt. So if you want to use 9 in a number, you have to convert from the character to a number. This would be the number 9. This is character 9. Again, we have another data format which is very useful, which is called BCD or binary coded decimal, which has a range from 0 to 9, and we use 4 bits to represent a BCD number, right? So BCD 0 is 0000 and BCD 9 is 1001 because we have 8, 4, 2, 1 code. As far as BCD is concerned, there are two flavors. There is the packed version of BCD and the unpacked version of the BCD. In the packed version of the BCD, since one BCD digit is 4 bits, so we have 2 numbers in a byte. So two characters in a byte, or 2 numbers in a byte. For example, if you want to store 12 in packed form, we would store it like this: 0001, which is the BCD code for 1, followed by 0010, which is the BCD code of 2. The 12 would be saved as 001, 0010. So 2 numbers in a byte of 8 bits. But if it is stored in unpacked, right? In unpacked, it is stored one digit at a time. So 1 is stored as 00000001. So this is the code for 1, followed by 000010, which is the code for 2. So this is the unpacked version. So 2 bytes required for 2 digits. In this one, 1 byte required for 2 digits. Again, what are the advantages of packed BCD? Less memory space required. Similarly, unpacked has the disadvantage that we require more memory space. Similarly, 623 would be stored in packed form by converting it first to 0623. So 0623. So for 4 digits we require 2 bytes of packed BCD because 1 byte stores 2 BCD digits. Similarly, if we want to store 623 in unpacked form, it would be stored as 623. 3 bytes required. Again, for storing 4 digits, the packed version is more memory efficient as compared to the unpacked version. Similar is the third example. Please do it yourself. Then the most famous binary coded hexadecimal, or BCH, binary coded hexadecimal is BCD, and binary coded hex is termed as BCH. And how do we do that? We have 16 digits of hexadecimal from 0 to 15 or 0 to F, and they are encoded using 4 bits. So 0000 for digit 0, and 1111 for digit F of the BCH, binary coded hexadecimal. Now we can talk a little about complements, and we know that negative numbers are usually stored in complement form, which is actually 2's complement is used. So what is the method for converting a number in 2's complement form? The easiest is to take the number and start from right towards the left, right? Write all the digits as they are up to the first one, right? So to form the 2's complement, it is really easy. We would start from the right and we will be moving towards the left. So we copy all the bits as they are up to the first one we encounter, and after this digit we are going to be complementing all the other digits. Okay, so 0 we copy it as it is, 0 as it is, 0 as it is, first one as it is. Now all these bits would be complemented because they are after this one. So 0 becomes 1, 0, 1, 1, 0, 0, 1. So this is basically our 2's complement number. Okay, some points about the computer data storage. We'll have the byte-sized data, which is 8 bits, and is declared by the define byte or the DB assembly language directive. And the byte-sized variable can be signed or signed. So for the signed numbers, we have these weights, right? So this is MSB is 128. It is actually 2 raised to power 0, 2 raised to power 1, and similarly 2 raised to power 7, which is basically 128. But for signed ones, this bit basically is the signed bit, which is minus 128, and the other bits have the notations 1, 2, 4, 8, 16, 32, and 64. So 2's complement is negative of a number, right? So this is basically what we are going to be finding out, right? Now let's say we have this decimal number plus 72, right? So why is that decimal number plus 72? When we convert it from decimal to binary, we have the 0100 1000. Now let's plug this pattern into our bits representation, right? So what we can do is that we can go back over here. It is 0100. So 0100, and it is 1000. So what is it turns out to be 64 plus 8, which is plus 72. Okay. So now, what was the 2's complement that we have? This is 1011 and 1000. How did we get it? We got it by this exercise. Remember this exercise? Yes. So once we have got this, now let's plug it in our signed number representation, which is 1011, 1011, and 1000, 1000, right? So what would be the number? How we can find it? It would be minus 128 plus 32 plus 16 plus 8. Okay, let's add all these numbers together. So what's this number? This total comes out to be minus 72. So this was the original number, which was plus 72. When we took 2's complement, we got this number, which is minus 72. So we agree that 2's complement is negative of the number. So what would happen when we add these numbers together? 0, 0, 0, 0, carry 1, again 0, carry 1, 0, carry 1, 0, carry 1, and 0 and carry 1. So this carry would be ignored, and this would be basically the 0 result we are talking about. So addition gives 0 because this number, which was the 2's complement, is negative of the number which was plus 72. Now some points about computer data storage. Again, additional points. Word size data defined by defined word directive can be signed and unsigned and stored in little endian form. And little endian is basically low byte followed by high byte. So this is basically the situation. Now, is it a signed word or an unsigned word? It is unsigned word. So let's suppose we want to store a word 1, 2, 3, 4 hex, H, right? So it consists of 2 bytes. In one byte 1, 2 would be stored, and in the second byte 3, 4 would be stored. Now this byte is called as the low byte, and this byte is called as the high byte. So what little endian would do is that this is the memory address or memory locations as they are going in hex, right? So first of all, in the lower location 3000H, the low byte would be stored first, which is 34H, and in the next consecutive higher location, which is 3001 hex, the high byte or 12H would be stored. So low byte followed by high byte. This is basically little endian storage. There are many processors that use big endian for that matter, but Intel family uses the little endian. Let's talk a little about the flags. We have the carry flag, with the C flag which holds the carry after the addition or the borrow after the subtraction. Then we have the parity flag, which is logic 0 for odd parity and a logic 1 for even parity. Parity is the count of ones in a number. It can be accessed as even or odd. For example, if we have 0, 0, 0, 0, 0, 0, 0, 1. Now the parity is odd because number of ones is 1, which is an odd number. On the other hand, if we have this 1, 0, 0, 0, 0, 0, 0, 1. So how many total number of ones do we have? 2, which is even. So this is now even parity. This is odd parity, this is even parity. So for odd parity, this flag would be 0, and for even parity, this flag would be 1. Let's have a demonstration of carry, which is very interesting. Okay, so if we add these two 8-bit numbers together, 0, 0, 0, 0, 0, 0, 0, 1 plus 1 is 0, carry 1, and this is basically 1. Now this is basically the carry. This is a demonstration of parity, right? In this number, the parity is odd, so parity flag is 0. In this number, the parity is even, so this flag is 1, right? So how parity can be used? Parity can be used for a number of ways. It is basically used for detection of errors in storage. Parity is a very simple scheme, and you would be surprised that memory chips of today would use parity for checking off the data, whether the data is correct or not. Some flags, some more flags. Auxiliary carry. Auxiliary carry holds the carry half carry after addition or borrow after subtraction between bit positions 3 and 4. So if we have a bit position from bit 3 to bit 4, then we have an auxiliary carry, and it is basically very useful for binary coded decimal or BCD addition or BCD subtraction, right? Subtraction. It means if we have an auxiliary carry, the result of BCD addition or a result of BCD subtraction would not be correct. So we must make a correction. So we'll check for auxiliary carry. Auxiliary carry means the BCD addition was error or BCD subtraction was error. Then the zero flag is very simple. The zero flag shows the result of an arithmetic and logic operation is 0. If the result is 0, Z is 1. Otherwise the zero flag is 0 if the result is not 0. So we can have certain instructions that can be used for jumping or branching. If we execute something like JZ, jump if 0, 0 underscore label, right? So if the result was of the previous operation was 0, which means the zero flag was 1, then this would be true and we would jump to this label. If the result is not 0, we won't jump to this label. We won't jump to this label because this is false. We'll execute the next instruction. So can anyone guess what would happen in a JNZ instruction?